In part 2 of Venn diagrams and set operations with 3 sets, we're going to look at some specific examples. So we're kind of going a little bit backwards. But we're going to look at Venn diagrams that represent sets that have specific numerical values in them. And we're going to determine what elements are in the different sets and the different sets based on set operations. Okay, so let's take a look at our first example. We have this rectangle that, remember, that represents our universal set. The universal set is every value that is inside this entire diagram. Most of the time, your My Math Lab homework tells you to write these in ascending order. That means starting from smallest to largest. I want to make sure you understand that because you might be getting something wrong if you don't put them in that order and they told you to. Now, it's not necessary when you're handwriting problems to put it in numerical or ascending order, but because your My Math Lab wants us to do it, we'll do it right now. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So I'm just going to write the numbers 1, 2, 3. In roster form, I can use an ellipsis to show that it keeps going all the way up to 15 and follows that up by 1 pattern each time. In set A, we have the elements that are contained in this red circle. And so those elements are 1, 2, 3, 4, 6, 9, and 10. Notice I did not use an ellipsis on this one because there's not a clearly defined pattern throughout all of it. Okay, for set B, we have everything in this purple circle. So that includes 1, 3, 4, 9, 13, 14, and 15. So that's just identifying what's in those specific sets. For A complement, remember that is everything in the universal set that is not in A. So based on our shading we did in the previous video, I'm going to shade that region. It's everything except for what's in A. So those values are what's in the universal set, but not in any of the other sets. So 5, 7, 8. And then everything in B and C that is not in A. So 11, 12, 13, 14, 15. Okay. Sorry, I ran out I ran out of room on the right side, so it's kind of squished. Anyway, B complement is everything in the universal set that isn't in set B. So again, I'm going to shade that. So it's essentially everything in the rectangle except for the circle that is B. So that includes the values 2, 6, or I guess if I go in order, 2, 5, 6, 7, 8, 10, 11, 12. Wanted to make sure I got them all. Okay, so we're just remembering the shading from the previous video can really help us figure out what we're actually looking at. And using that sheet, you can actually use it to help you find and figure out a lot of these problems. So now we're going to look at some set differences. We're going to do B minus C. So remember, that is everything that is in set B except for those that are in C. So we cut out C and we only shade the part that's in B without being in C. So the values in that set are 4 and 13. So then C minus set B is everything in C except for anything that's in set B. So that's going to be these values that I've shaded. So that includes 2, 6, 11, and 12. Now we're going to look at the intersection of two sets, A and B, that's where they overlap. We can only count the elements that are in both A and in B. So I look where A and B overlap. That's this overlapping piece right here between the circle A and the circle B, and that's what I shade. So the values for this one are 1, 3, 4, and 9. I thought of something to tell y'all. Hopefully it's not too late. But I always remember that the U is union because union starts with U. So if you're ever like, wait, is this one the union or the intersection? Look at the symbol. If the symbol is a U itself, like that, then it's a union. If it's upside down, then it's in the intersection. I don't know if that helps, but okay. The union of the two sets A and B is everything from set A and set B included. So essentially we just get to outline all of set A and set B, and it's everything in this happy conjoined circle. So, or two circles. So here we have 1, 2, 3, 4, 6, 9, and 10, and 13, and 14, and 15. So that's the union of A and B. Now we're going to look at what's the intersection of A with B intersected with C. So we can do this in order. If I think about this, and I'm going to do a light gray, A intersect B is this area right here that we just saw. But then we have to intersect that with C. And so we can only include the elements if they are in all three of these. So that is this section right here. Okay, so the intersection of all three groups is just whatever's in that region 5. So the elements in the intersection of A, B, and C in this example are 1, 3, and 9. Now, the union of the three sets is everything contained in any of the three sets A, B, and C. So we already saw that we had A and B for the union of A and B, right? But this also unions it with C. So it's everything in this happy, almost Mickey Mouse looking thing. So I need a lot more space to write the elements of this set because there's a lot of them. Essentially, it's everything in the universal set except for 5, 7, and 8. And our universal set was the numbers 1 through 15. So I'm just going to write 1 through 15, but not include 5, 7, and 8. So 1, 2, 3, 4, 6, 9, 10, 11, 12, 13, 14, 15. And that is the union of our three sets. Now again, the shading video hopefully will help you figure out the values for each of these sets. For this next one, we're going to be looking at A minus C complement. So the complement of A minus C. Following the order of operations, we need to find out what A minus C is first. So what I've done is on the side, I've shaded in what A minus C looks like. Remember, it's everything in A that is not in C. Okay, so that's our region for A minus C, but then the complement of that is everything kind of like the opposite, everything else that remains. So to shade that in darker gray, the complement of this, A minus C complement, is everything that's shaded in the gray. So it's essentially all the regions except for regions 1 and 2. So I'm going to count all the elements in all of these regions except for 1 and 2. And that's A minus C, that's complement. So here we go. That includes 1, 2, 3, 5, 6, 7, 8, 9, 11, 12, 13, 14, and 15. Okay, so it helps to do these in pieces and show each step. Okay, so A minus C complement. Let's check A complement minus C complement. Based on our shading video, we saw that A complement minus C complement is equal to the space that's shaded in this small diagram. So these include the elements 11, 12, 13, 14. No, 11, 12, 14, 15. These right here. Just a quick reminder, I'm human. So recall that if two sets are equal, they have exactly the same elements. So at the end of the shading video, I asked you to check out for yourself to see if A minus C complement was equal to A complement minus C complement. And now we have one specific example. We used a specific case and we found a specific example that provides us with a counterexample. So we can definitively say that these two are not equal based on inductive reasoning. We had a general case. Now, looking at the shading, if I ignored all the numbers and just looked at the shading, that would be a deductive way of showing that they are not equal. They would not have the same elements because they don't include the same regions. So let's consider this problem. Can I say the following? A intersect B complement is equal to A complement intersected with B complement. Is this true? I like to put a little question mark over my equal sign if I haven't proven something to be true, because I don't like to say things that are wrong. So the way we can show this, and the way we can definitively show that this is or isn't true, is we could use Venn diagrams and shading to do so. Or I can look at the set above, and if I show that they're not equal, then I can definitively say that I have a counterexample, so we know that that's not always true. Okay? So we can do that with the previous example and see if we get a counterexample. So let's look at the first one. A intersect B, but the complement of that. So first off, let's look at this. A intersect B is these two regions right here. So the complement of that is everything else. So I'm going to say, okay, that's this all the way outside out here. Okay, so A intersect B, the complement of that is equal to the set 2, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15. So then we look at A complement intersected with B complement. So A complement, I'm going to shade in light gray. Remember, it's everything in the universal set that is not in A. And in dark gray, I'm going to do B complement, which is everything in the universal set except for B. And the intersection of those two things is going to be what shaded both colors. Okay, so that's going to be these regions right here. So that gives us the set 5, 7, 8, 11, 12. And we now have a counterexample because these two sets are not the same. So, therefore, with that counterexample, we can show that that is not always true. Now, let's do the same thing with the unions and see what we get. So A union B is everything within A and all the elements in B. So we count it if it's either in A or in B. So that gives us these. So the complement of that is everything that in the universal set that we did not shade. So that's going to give us 5, 7, 8, 11, and 12. Hopefully your mind is kind of thinking, wait, what? We'll take a look and see what's happening in just a second. So let's look at the union of the complements. So when I say these phrases, the first one that we just did, I would call that the complement of the union. And this right here, I would call the union of the complements. So think about that. The complement of the union. Okay? The complement of the union versus the union of the complements. That's just the way I like to phrase it. So hopefully you understand where I'm coming from. So A complement is all the stuff that's not in A. B complement is everything that's not in B. And the union includes everything from either one of those. As long as it was shaded, it gets included. So anything that's shaded with the light gray or the dark gray would be included. So the only things that aren't included are pretty much 1, 3, 4, and 9. I want to make sure I get that. Okay, so let's write that out. Again, that's all the number values 1 through 15 without 1, 3, 4, or 9. Now, take a look at these. I'm going to go back and forth between the last two slides. The complement of the intersection actually matches the union of the complements. So let me circle that in red. This set right here is equal to this set right here. And then the intersection of the complements right here in blue is equal to the complement of the unions. So that we have not proved that. We have not proven it. We've just given a specific example. In order for us to prove it, we would need to use deductive reasoning. So I could claim, we know that this isn't true. I showed that wasn't true. But what about this? Can we say that the complement of the intersection is equal to the union of the complements? And can we say that the complement of the union is equal to the intersection of the complements? Okay. We have a specific example for this one. We have a specific example for this one where it worked. Okay. But we have not proven that it's true, because all we would need would be one counterexample to prove that it was false. So we've used inductive reasoning to say that we kind of believe that this might be true, okay, because we saw a specific example where it worked. So we said, okay, the specific example worked here, and the specific example worked here. But we would need to use deductive reasoning to show that this is true all the time. And we would use shading to do that on Venn diagrams. Now, when you do the shading, we would want to make sure that we show it on separate diagrams so that we can actually see what's going on. So here, I'm going to do the parentheses in red. So the intersection of A and B is this little piece right here. Okay, so the complement of that, which I'm going to shade in red, is everything else in the universal set except for that piece right there. So everything that's in B that isn't shared with A, everything that's A that isn't shared with B, everything in C that isn't shared in A and B. So essentially it's all of the regions except for region 2 and region 5. Now, on this one below, we're going to do the complement of A union with the complement of B. So the complement of A, I'm going to do in light gray. It's everything in the universal set except for A. In dark gray, I'm going to do the complement of B, which is everything in the universal set except for that circle and loop containing the elements of B. Okay, and the union is everything that's touched by either of those shadings. If it's an element of the light gray, it counts. If it's an element of the dark gray, it counts. And so if you notice here, I'm going to shade this all in blue. The only piece that isn't shaded is that same one. So we can show in general that this is true. These two sets are equal. We call this De Morgan's law. And you can think about it as when I have this right here on the left, if I distribute this complement out to each of those sets, it changes this into a union instead of an intersection. So that's kind of one way to think about it. That's almost like an algebraic way to think about it. How does distribution of complements in parentheses impact a set and their set operation? Okay, so try on your own to shade to figure out if the other one is true. That's the A union B complement. Is that equal to A complement intersect B complement? Which is the other part of De Morgan's law, so that should kind of give you a hint of what should happen. But this is De Morgan's law, and you're going to see it used in your homework. It's going to ask you if you can verify that these things are true just based on looking at specific examples. All right, so that is section 2.4. We saw the shading. The shading helps a lot with determining what sets you're talking about, but the shading is really important in being able to prove conjectures about set equality. So thank you so much. If you need help with anything, be sure to email me and let me know. Thank you.